Let's now have a look at applications of calculus to the physical world. So basically we want to look at motion here in a bit more detail. So some terminology. Remember, we've now got this thing called displacement. It's the same as distance, but with direction. So now the plus or minus means something. Velocity, we can symbolise that with V. Dx to t, because it is the derivative, the rate of change of displacement with respect to time. And the dot notation for the derivative, we keep that for motion. So in motion, we sometimes use the dot notation. It's the rate of change of the displacement with respect to time. So it's the speed, but now the plus or minus has some meaning. Which direction is it travelling in? And then acceleration, well, A for acceleration, it's the rate of change of velocity with respect to time. So dv to t. It would be the second derivative of displacement. So d2x to t2, or we could have x with 2 dots, or velocity with 1 dot. So the rate of change of velocity with respect to time. Now, I just want to make a point here about this term called deceleration. If you hear someone saying deceleration, there is no such thing as deceleration. What it is when something's slowing down. It is still accelerating, but it's accelerating in the opposite direction to which you are travelling. So imagine someone is either pushing you or pulling you back. If I'm travelling in the positive direction and someone pushes me in the positive direction, I'm going to get faster, I'm going to accelerate. But if I was moving in the positive direction and someone grabs my shirt and pulls me back, I'm going to slow down. But I don't have to be moving in the positive direction for that to happen. If I was travelling in the negative direction, but then someone pushes me in the negative direction, I will speed up. So negative acceleration does not mean slowing down, because in this instance, it's in the same direction as our velocity, and it's speeding up. And similarly, if I'm moving in the negative direction, someone grabs my shirt and pulls me in the positive direction, I will slow down. So slowing down is when acceleration is in the opposite direction to velocity. Speeding up is when we're in the same direction. Here is a displacement time graph. Now, because it is a displacement time graph, my travel graph could now have negative values on the vertical axis. And what we saw was that the tangent at any particular point will give us the instantaneous velocity. So the slope of that will be the instantaneous velocity, the thing that's happening at that exact point in time. Now underneath that, I'm going to draw the velocity graph. Now I could draw it by bringing down key features. So for instance, when the displacement curve has a stationary point, I know that with velocity graph it will be 0 and things like that. We'll end up with, well, it looks like a parabola for this particular situation. Now, same deal, if I was to draw in a tangent, that would be the instantaneous rate of change of velocity. So in other words, acceleration. So the slope of that line would be the instantaneous acceleration. Now, to complete the set, if I was to draw the acceleration graph, well, I'd end up here with this straight line. Now, it makes sense. If you look at the displacement graph, that looks like a cubic. Differentiate a cubic, you get a quadratic. Differentiate a quadratic, you get a linear function. We'll look at how to draw those in a bit more detail later. But reading off my graph, if I had to find the distance travelled, well, I can look at my displacement graph and I can see I've gone up to 2, then travelled all the way to -2, but then back up to -1. That would be 7 meters. It would also equal the integral going from 0 to 1 minus the integral going from 1 to 3, because it's below the axis, plus the integral from 3 to 4. So we could do it that way now. Total displacement, well, I started at 0, I ended at -1, so it's -1. If I was to use the velocity graph, it would be the integral all the way from 0 to 4 in one hit. So distance is like when we find the area. So work out what's above and what's below. Displacement would be the complete integral. Average speed. Well, we just said the distance travelled was 7 in 4 seconds, so 7 divided by 4, well, I'll leave that as an improper fraction. Average velocity will be -1 over 4, so -1/4. Right, we don't actually need the graph now. If we know the formula for one of these, we should be able to work it out. So we've been told the displacement, it's still a cubic like the picture we did before, but we've been given its equation, t cubed minus 21 squared. Find the acceleration at time t. In other words, what's the formula for acceleration? I just differentiate it a couple of times. Differentiate once, I get velocity. Differentiate a second time, I get acceleration. So 6t minus 42. Find when the particle is stationary. If it's stationary, I'm finding the stationary points of my displacement graph. That's when the derivative is equal to 0. Well, the derivative is velocity, so there's another way of thinking about it. When is it stationary? It's when there's no velocity. Velocity is 0. So solving that, we've got a quadratic there. So initially at t equals 0, and again after 14 seconds. All right, new problem. This time we've been given the acceleration. So the particle is moving on the x-axis again. So most of the stuff we're looking at is just straight line motion. It starts at t equals 0, but it starts not at the origin this time, but at x equals 7. Its acceleration is given by the formula 2 plus 6t. We want to find the position when t equals 3, so after 3 seconds. So acceleration, 2 plus 6t. Velocity, we would integrate. Don't forget your constant. Now, there should be some information in there that allows me to work out the constant. And it said started from rest. So when t equals 0, velocity is also 0. Sub that in. Our constant in this case is 0. So we would have got away with it if we got the constant, but that was just lucky. So v is 2t plus 3t squared. All right, integrate that to get displacement. T squared plus t cubed plus a constant. Again, we're looking for information that links time and displacement. And there it is at t equals 0. So when it starts, we're starting at the point x equals 7. Sub it in, we get that the constant is 7. So in this case, I wouldn't have got away with forgetting the constant. So x equals t squared plus t cubed plus 7. We want the position when t equals 3. Now it's just a substitution question. When t equals 3, x is 43. Now how do you want to answer it? Well, you could just say it's x equals 43, or you could talk about the actual particle itself and say, well, look, after 3, I know it's 43 units. Displacement was positive, so I know it's to the right of the origin. It's moving in the positive direction. Another way I could have done this. All right, acceleration is dv to t. I can do it as a definite integral. That saves any problems with the constant. But to do it as an integral, remember, when we integrate, we separate the variables. So the integral of dv would equal the integral of 2 plus 6t dt. And we match the limits. When t equals 0, velocity is 0. And at the top of the integral, we want to find, well, we want to find an equation that links t and v. So I just use those pronumerals. So integrate, well, the integral of dv is just v. Substituting v minus 0, we can just write v for that. Right-hand side, 2t plus 3t squared. Sub in t, sub in 0, and we get 2t plus 3t squared. Now for dx to t, separate the variables. We were told that at t equals 0, x was 7. So they'll be the lower limits of my integral. When t is 3, so that's the upper limit, what's x? Now, because it's not going from 0 to v nicely like the last one, I can't just write down v, or in this case x. I've got a definite integral. It integrates to be x. Subbing in from 7 to x, we get x minus 7. And on the right-hand side, sub in 3, sub in 0, move it all to the other side, and there's my answer, 43. So as I say, by doing it as a definite integral, I don't have to worry about the constant. It works it out for me. Let's look at an HSC question. So 2001. Wow, it's moving such that x equals t minus 2 on t plus 2. And t is measured in seconds. So what's the displacement when t is equal to 0? Well, that's just a substitution question. So it's -1. So it's 1 metre to the left of the origin, or x equals -1, however you want to write that answer. Show that x equals 1 minus 4 on t plus 2. Well, that's just an algebraic fraction. So I'll play around with that, and I'll common denominator of t plus 2, And sure enough, look at that. We get the 1 minus 4 on t plus 2 is indeed the same as t minus 2 on t plus 2. So I've shown that. Hence find the velocity and the acceleration. So differentiate displacement, we'll get velocity. I'll use my reciprocal rule for this one, minus the derivative on the function squared. And differentiate again, and we get acceleration. So minus 8 on t plus 2 all cubed. Is the particle ever at rest? Well, there's my velocity formula. Can that equal 0? No. We've got a constant on the top of the fraction. It is impossible for that to equal 0. So therefore, the particle is never at rest. What is the limiting velocity? So if we could keep going on forever, so what is the limit as t approaches infinity of the velocity? Well, we said velocity was 4 on t plus 2 all squared. What is the limit as that approaches infinity? Well, it's 0. Of course, you could think of it graphically. If you were to draw 4 on t plus 2 squared, you would get this piece of the hyperbola there, and we can clearly see that as t is getting bigger and bigger and bigger, our curve is getting closer and closer to the axis, or 0. So whichever way you do it, the limiting velocity of the particle is 0 meters per second. Here's another one. This time, displacement is given by a trig equation, sine 2t plus 3. Sketch it. So we've got to sketch a trig graph. So I know the amplitude is 1. It's been shifted up 3 units. Period 2 pi over the coefficient of t, which is 2, so pi. I'll mark my divisions off every pi on 4. Now they want me to go from 0 to 2 pi. The amplitude's 1, but it's shifted up 3, so I'll mark in up to 4. I'm just going to draw in, I've dotted it in, but just so I've got to place a reference point to plot my points, we've shifted the axis up 3. Now, the sine curve would normally start at the origin, but I've shifted it up to 3, so I'll plot that point in. Then the sine curve would go up 1, down, down, up, and so on and so on. Draw a nice neat curve, and there we have the graph that they're looking for. Using our graph, or otherwise, find when the particle is at rest and the position at those times. Now, the graph's going to make life a lot easier, so I don't have to actually use calculus here because I know the particle is at rest when the velocity is 0, but that is the derivative is equal to 0. So I'm looking for the stationary points. So I just look at my graph for the stationary point. So at t equals pi and 4, we have a stationary point. Its displacement is 4 meters at that point. Next one, 3 pi and 4. Next one, 5 pi and 4, 7 pi and 4. So much quicker than using the calculus. So I take advantage of the graph that we had drawn. And they gave us the hint by saying, using your graph. Describe the motion. Wow, this is where you get to have fun. So what did I say? I said, I used a big word there, oscillate. The particle oscillates between 2 and 4 with a period of pi seconds. So you're describing what your particle is doing there. Let's have a go at 9b.